Okay, everybody take your seats, settle down, finish your conversations, come back from the bathroom, come back from beverages. Enjoy the end of your coffee break being over and more exciting talks for Student Day. I will continue to ramble as you sit down, and you will hear my voice no longer once you are silent and sitting down. That is the threat. You'll be like, wow, Aiden finally shuts up when we are sitting down. I will continue to keep talking and continue to keep talking until you're all sitting down and done, and it will be exciting. So our next speaker is Jackson Gendreau from University of Colorado Boulder, talking our first CEDAR regime about the mesosphere, lower thermosphere, and we look forward to his wonderful talk. Good luck, Jackson.
Give me a second, yeah. Gotcha. Okay, awesome. Hello, yeah, I'm Jackson Gendreau. I'm from the University of Colorado Boulder. This is probably my 4th or 5th CEDAR conference so far, if you count the online COVID ones. And I'm gonna be talking to you about the MLT. Now, the mesosphere and lower thermosphere is a little bit lower in the altitude range, and I think a lot of you guys work in, but that's part of the reason I wanted to introduce this region, was to just show off some of these features that are in this region that you may not be familiar with. And then ultimately my goal is to emphasize to you, whether you work in this region or not, why you should at least know what's going on here. So yeah, like I said, I'm going to try to hopefully provide some context for some of the talks you might hear this week and some of the terms you'll encounter. Introduce the coupled nature of this system, yes, all the way down to the surface, as though I'm going to argue that this coupling exists, and I'm going to introduce some of these unique features. So to define the MLT, the mesosphere and lower thermosphere, it's what it sounds like. It's generally the mesosphere and lower thermosphere. But the reason these regions often get wrapped up into this unique, under this unique title is because there's a lot of features in the mesosphere that are also relevant in this lower region of the thermosphere, those being some of the dynamics I'm going to introduce. So if I'm going to introduce, real quick, we're going to run through this, what the main drivers, this is my opinion at least, on what some of the main drivers are of each of these regions going from the surface up. Troposphere is strongly driven by surface interactions and moisture in the atmosphere. The stratosphere, strongly driven by solar heating due to ozone and planetary waves. The mesosphere is largely based on wave dynamics that drive it to deviate away from radiative equilibrium, which is going to be what I'm talking about a lot here. And in the thermosphere, it's where you start to get electrodynamics, and you have a non-mixed atmosphere that drives some more dynamics in that region. Ultimately, it's this thermal structure that generally defines these different regions, where the stratosphere ends at, does this have a pointer? Maybe? Okay, cool. So the troposphere is generally defined to end around where this temperature stops cooling. The stratosphere is defined about where this stratopause is, where the temperature stops heating again. The mesopause is determined by where the temperature cools again. So each of these temperature inflection points generally defines some of these, where these regions are. So the first feature I want to talk about in the MLT region are the metal layers. If you know the research my group does, we focus a lot on these metal layers. But these are metal layers in the atmosphere that are permanent and global, found everywhere around the globe. And their source is from ablated meteors and cosmic dust. So when you see a shooting star burning up in the atmosphere, it is depositing metal that is stored in these metal layers. They're not permanent. This metal is not permanently there. It is consumed by chemistry and slowly descends, but it's also resupplied by more cosmic dust and meteors. The metal species that comprise this layer are all these different ones I've listed on the screen: iron, sodium, potassium, calcium, and others. And just want to mention also that there's actually somewhat recently discovered man-made metal layers in the in the stratosphere from satellites that are burning up, but that's a different story. These can be observed by LIDAR, meteor radar, and even some of the air glow you see, like the sodium air glow is a very strong layer as well. And you can see a couple pictures of how these metal layers can also be extended up into the thermosphere by various electrodynamic and dynamical processes. Next feature I wanted to talk about, see if this video plays, awesome, is air glow. Air glow, first thing I want to say is air glow it is not auroral, it is not scattering, it is not thermal emission. What it is it is the result of chemiluminescent processes. And so you can see that permanent air glow layer. I put a video because it's a little easier to distinguish it from surface lights. But you can see that is a permanent, pretty thin layer that we're seeing here. What's nice about air glow is that it is altitude resolvable. We know the location of these different species that are emitting this air glow. Thus, if we can observe them, we know exactly what altitude that came from. So air glow can be used for temperature and wind measurements using FPIs, and you can do wave observations by using various types of imagers. Like you can see here from the AWE instrument mounted on the ISS, they were able to observe gravity waves coming off of a hurricane last year. Yes. I'll let that video finish. Okay. Another feature in the MLT that's unique to this region is noctilucent clouds, or polar mesospheric clouds. Now, polar mesospheric clouds are the highest altitude ice clouds in the atmosphere, in all of Earth's atmosphere. They form around the summer mesopause, which is the coldest region of Earth's atmosphere, which I will be explaining how that occurs later. And what these are essentially, the reason called noctilucent clouds is because they look like they are glowing at night. And you can see my little diagram up there that shows how that occurs, just due to the angle of the sun still striking these clouds while the surface is in darkness. You may have even seen these if you've been at reasonably high latitudes. They're called polar. You don't necessarily need to be at polar latitudes to see them. Few fun things about PMCs is they were first, it often gets reported that their first observation, but I think this is probably just the first recorded observation, was after the Krakatoa volcano erupted. It emitted water vapor all the way up into the mesosphere. And that's when these were first observed, and that's when we started to realize that we could use these as tracers. These are the first tracers that we were able to observe the mesosphere with. And this water, I want to mention, is not solely transported up from below. Some of it is, but it is also released from chemical reactions. So finally, the turbopause. The reason I put this in quotes is because the turbopause is debatably an outdated concept, but essentially it's somewhere in this region in the MLT, the atmosphere transitions from what we call well-mixed to being diffusive, defined by molecular diffusion processes. But it is not necessarily a sharp point. It occurs somewhere between 100 and 120 kilometers, where again, below that region, the atmosphere is well mixed, where atmospheric constituents are in a relatively predetermined ratio, and above that, they become diffused. It can be defined by a few different things, like the argon to N2 ratio, and molecular versus diffusive time constituents, or time constants, sorry. So there's quite a few different ways that you can observe the MLT. From the ground, you can use LiDAR, radar, imagers, FPIs. Satellite can use a lot of the instruments as well, in addition to limb scanning procedures. All of these ground-based things can also be mounted on airplanes or seaborne instruments. And you can also use in situ methods like sounding rockets, and reentry drag is also a way you can observe different parameters of this region of the atmosphere. The reason I wanted to mention all of these is because the MLT, one of the other things that makes it unique is it is too high for you to use stratospheric balloons, and it is too low for most satellite-based things to study. So it's a pretty difficult region of Earth's atmosphere to study. A couple different instrumentations that you can use to observe these are, again, like I said, LiDAR. There's resonance fluorescence processes like my group does. There's Rayleigh scattering processes. There's all different types of radar, imagers, and FPIs that can study this. So to just dig into a little bit, one of these methods, the one that I'm qualified to talk about, is LiDAR. What's special about LiDAR is that you can observe any molecular atom-species that has a favorable absorption spectra. So what I mean by favorable absorption spectra is that the atmosphere is transparent, meaning that the atmosphere doesn't suck up your laser beam before it reaches your constituent you're trying to probe, and that there is an existing laser system that can reach that frequency. There's a picture of me at Antarctica running our LiDAR system. That's that's proving my qualifications to talk about LiDAR here. And then also, yeah, so like I said, the pros of it is very high resolution, gives you altitude resolved measurements of whatever it is you're studying, and it's also very sensitive, so you can use it to study very sensitive things like these metal layers I mentioned. If you look at that picture in the bottom right there, you can see some LiDAR data that was collected by Yingfei Chen. He's one of our students, and he's in here somewhere. You can see the gravity waves in this that I'm going to talk about in a few slides here. Some of the cons of LiDAR is that it's compared to a lot of other types of instruments, not necessarily like a satellite, for example, but other ground-based instruments, it's often much more expensive and more complex and more sensitive to disturbances than other observation methods. So let me get into what I study a lot is gravity waves. I'm going to introduce the concept of these gravity waves and why they're relevant to the MLT as a main driving feature. So first thing I want to talk about is different types of atmospheric waves. Throughout the atmosphere, there's all different types of waves. Some of the most important ones are tides, which I'm sure you're familiar with, planetary waves, and gravity waves. Now, what I will say is what gravity waves are not is gravitational waves. I feel like a lot of you gym people might be more familiar with gravitational waves, which are the waves that emerge from black hole, the very deep space phenomena. These are very different. They might better be called buoyancy waves. So what gravity waves are generated usually in the troposphere from disturbances to Earth's stratified atmosphere. So for example, flow over orography like mountains or continental shelves will generate gravity waves. Things like earthquakes, explosions, hurricanes and volcanoes will also generate gravity waves. And they can also be generated at higher altitudes by things like deep convection or even joule heating by the aurora may cause gravity waves. So just to introduce gravity waves maybe in a way that might be familiar with, the restoring force for gravity waves is atmospheric buoyancy. That is a parcel of air gets displaced to a point where it is not neutrally buoyant and it returns, and that oscillation process generates your wave, which is able to propagate through the atmosphere. Other waves, to compare their restoring forces, you might be familiar with Langmuir waves and plasma. They have a different restoring force, that's the electric field from the displaced ions. And planetary waves, their restoring force is conservation of potential vorticity. So just to compare these waves mechanisms versus other wave mechanisms. So we know gravity waves. What's nice is we know gravity waves when at least we're talking about the linear interactions they undergo. We know that they behave a specific set of essentially rules, dispersion and polarization relations that determine the relation of the various parameters of the gravity waves. We also know that these gravity waves, as they propagate through the atmosphere upwards, from the ground upwards, they generally increase in amplitude as they go. Now, if these gravity waves get strong enough or encounter instabilities in the atmosphere, or different wave-wave interactions can actually cause these gravity waves to break and dissipate their energy into the mean flow. Now, when these waves break, they generate turbulence, they heat the atmosphere, and like I said, they exert that forcing on the atmosphere. So how high up can these gravity waves go? They can go pretty high. I don't even think we know the full extent of where these waves go. Like I said, once you get past the mesopods, it gets more difficult to observe these. But processes like wave breaking in the atmosphere can extend the range of influence of these waves to much higher altitudes than we previously thought before, and improving detection methods are letting us see these waves even higher. You can see here, this is an observation from our group over McMurdo of the atmospheric metal layers showing the features of these gravity waves reaching up to 160 kilometers, and there's even higher observations than this. So we don't truly know the full upper extent of these, but that's an active area of study. So how can you identify where these gravity waves came from? You can compare the parameters. If you see different parameters in two different regions, you might be able to conclude these are different wave sources. You can perform, like I said, we know the equations that govern the propagation of these waves, so we can occasionally trace these waves back to their source analytically. And then also, sometimes you can just look at the direction the waves are going. If you see waves propagating downwards, you know they were generated somewhere above that point. So now, to get into atmospheric dynamics, I want to just cover a few basic atmospheric dynamics that are going to help us interpret how these gravity waves affect the MLT region. So first, let's talk about adiabatic expansion. Adiabatic expansion is when you have an air parcel that's raised up in the air, it expands, and due to the work it does, it cools. Similarly, you have adiabatic contraction when a parcel is lowered in the atmosphere. And that's all just due to the ideal gas relation. You have pressure gradient flow, where air masses will generally flow away from a heated region. And Coriolis force, without getting too much into it, essentially in the northern hemisphere, it's sort of a pseudo force that causes a flow to turn to the right in the northern hemisphere and the left in the southern hemisphere. And for the relation I'm going to show on these next slides, I just want to emphasize as a sort of disclaimer that these are very simplified. These processes vary with latitude, longitude, they occur in 3D space. So these are simplified relations, but they can help paint a picture of how these gravity waves affect the MLT flow. So first, the troposphere is governed by equatorial heating. One of the main processes here gives you this poleward flow in the upper troposphere. Given that Coriolis force, you see these eastward flows that we see. In the stratosphere, where you have summer ozone heating, you in general get a summer to winter flow in portions of the stratosphere that give you this different zonal wind pattern. So if you take these wind patterns and you plot them onto split them by summer and winter flows, you'll see you get these different wind profiles. Now, gravity waves, they generally propagate against the wind, meaning that if you have gravity waves that are flowing westward like this, they are actually going to be filtered out by that wind. When the gravity waves encounter this wind, they're essentially, well, like I said, filtered. However, in the summertime, eastward gravity waves are able to propagate all the way up to the mesosphere. And in the wintertime, you have westward gravity waves that can deposit their drag, while eastward gravity waves are absorbed. Now, if we look at the gravity wave drag that's deposited there, we can see that in the wintertime, that gives us a westward flow. Summertime, a westward flow with that Coriolis, a poleward flow. Summertime also gives us a poleward flow. So ultimately, these gravity waves give us a poleward flow in the mesosphere. Now, just to real quick compare with some empirical models to show, I'm not just making all this up. You can see this is the CERA COSPAR model. We got eastward, westward, eastward flow. And then in the wintertime, we have this eastward, eastward, westward flow. So when we look at what this actually does in the greater picture of meridional flow, we get this, like I said, around the mesosphere, or rather around the mesopause, we get this poleward flow. Now, due to Earth's spherical geometry, that gives us polar vertical winds. And so what that means is at the winter pole, we get, at the summer pole, we get this upwelling that actually cools the mesopause. That's what gives us that super cool summer mesopause where these polar mesospheric clouds form. Similarly, this downwelling at the stratopause warms the stratopause and actually forms that wintertime stratopause, where normally the stratopause is formed by solar heating. Wintertime wouldn't have solar heating, so that summer stratopause is actually dynamic feature. Winter stratopause is a dynamic feature. So real quick, I just want to cover why some of this is more maybe relevant to you guys in GEM. I know a lot of GEM guys, people who study GEM are higher up outside of Earth's atmosphere, but if you're in the ionospheric side of things, or if you're on the CEDAR side of the ionosphere, these things will be relevant. So travel ionospheric disturbances. If you're not already familiar with these, you will definitely be after this conference. Very hot topic of study. TIDs, they are not necessarily gravity waves, but they share a lot of the same features with gravity waves, and I believe the community generally believes a lot of them are gravity waves. Signatures of gravity waves measured in ionospheric parameters. Traveling atmospheric disturbances are gravity waves measured in the same region, but from neutral species that we're measuring. And then plasma bubble seeding is also a very popular topic that is believed to be strongly formed by gravity waves. All of these topics are still, the role of gravity waves in these is still debated and actively being explored, but when you see these topics, TIDs, TADs, and plasma bubbles, think about gravity waves when you're looking at them. So the main thing I wanted to end on is just emphasize that this whole vertical space system is coupled. I introduced to you how the gravity waves reaching the mesopause are determined by the atmospheric flows below, and then here introduce how these gravity waves can affect what we observe above this mesopause point. So ultimately, the MLT is a unique region of wave interactions, chemical reactions, and plasma neutral coupling. These gravity waves are very important in the mesosphere, and these coupling processes link the lower atmospheric conditions to the features that we see in the ionosphere. So final thing I'll end on is, like I said, when you see these things, keep in mind how disturbances and changes in the lower atmosphere are actually going to affect what we observe in the TID. So you can't, in the MLT and above. So you can't observe these upper atmospheric regions without understanding what goes on below to some extent. I think that's it.
Thank you so much, Jackson, for that talk. Do we have any questions for him? I think Austin's going to get to you. Do we have anybody on this side of the room who I can get to for a second question?
Hey, that was a really cool talk. Thank you. I was just wondering, so you mentioned gravity waves breaking. When I think about like a breaking wave, I think about like a water wave that's getting into shallower water. I'm just wondering, what does that look like for an atmospheric gravity wave?
That's a good question. That's a pretty common analogy that's used, though the physics of those are an ocean wave we would call a surface wave. These are internal, like a surface gravity wave. We're looking at internal gravity waves. The dynamics are slightly different, but it is similar. They encounter unstable conditions at which point it deposits itself as turbulence and a forcing on the background. So there's relations, not the exact same features, but you can often picture it like that.
Thanks.
Yeah.
I may have just missed it. I didn't see it mentioned earlier. But are sounding rockets used for MIT studying in situ?
Yes, absolutely. They're one of the most powerful methods that you can do it because you can mount whatever kind of sensors you want on their LiDARs. You can even mount LiDARs on them too. Yeah, they're used a lot. Problem is that they are very temporally limited, right? You're only measuring for the few seconds that you're passing through the MLT. But they're a very powerful mechanism that's helped push that study of the MLT forwards a lot over the years.
Okay, we have time for one more question.
So the stratification seems like it plays a key role in having these vertical structures, just like you mentioned the internal waves like ocean, and it could reach because it's constantly stratified. Mm-hmm. So that is the case here. If there's a condition where it's continuously stratified, reaching far up, then you're going to expect to find the gravity waves like up in the higher.
Yes, yeah, absolutely. The whole, like I said, gravity waves, their propagation mechanism is completely based around buoyancy restoring force, and if you don't have this stratification in the atmosphere, you won't have this buoyancy existing. So very good note that this stratification is completely key to all of this.
Thank you.
Cool.
Thank you again, Jackson. Our next speaker is Brenner Royer-Smith, also from Powerhouse UC Boulder, here to speak on ionosphere-thermosphere.
Test this real quick. Okay, great. Hi, I'm Brenna. I am, as they said, a PhD student at CU Boulder, going into my 5th year. But this is my 3rd CEDAR, and I am here today to talk to you mostly about the ionosphere, just to give you a little tutorial if you're unfamiliar with it, and just hopefully help with some context of stuff you'll see at the conference. A heavy emphasis on overview because there are whole classes dedicated to the ionosphere, and I've got 20 minutes, so let's go. What is the ionosphere? By definition, it is a, quote, layer of the atmosphere that stretches from 50 kilometers all the way up to 1,000 kilometers. This is the layer that I like to say absorbs the sun's radiation and protects us from it, but it's just the layer that interacts with the high energy UV and X-ray waves from the sun, and they interact and collide with the molecules and the atoms in the atmosphere and lead to ionization. Ionization is just when an electron breaks free from a neutral atom or molecule and leads to the existence of positively charged ions and negatively charged electrons floating around, creating this like weakly charged plasma in our atmosphere. Due to all the different layers of the atmosphere and the different density of those layers, we get different layers of the ionosphere as well. So just as a quick little history lesson of how this came to be, it was first theorized that the ionosphere existed as early as 1839 by our guy Gauss. And in 1902 to 1912, people were noticing some weird propagation issues and limitations with their radio. And finally, in 1924 and 27, Appleton finally sort of proved the existence of the ionosphere, particularly the E region, I believe, was defined first, and did that doing a radio propagation experiment. So, as I said, the ionosphere is made up of layers, but since the ionosphere is influenced by the sun, these layers are a little different for the day side versus the night side. So first, looking at the day side, we're going to start with the D region at the bottom, roughly from 60 to 90 kilometers. This layer is rich in nitrogen, oxygen, water vapor, ionized usually by X-rays and Lyman alpha UV, usually mostly ionized during geomagnetic storms because it is the lowest and therefore densest layer of our atmosphere, which leads to faster recombination. Recombination just being the opposite of ionization when a free electron recombines with a positive ion and makes a molecule again. Next we have the E region in the middle from about 90 to 150 kilometers. This is also some oxygen and nitrogen, some NO plus at higher latitudes, primarily ionized by, now we're getting into some UV radiation and still some X-rays in there, reflecting middle and high frequency radio signals. And at the top, we've got the F region from about 150 to 400 and above kilometers. This region is actually made up of 2 layers during the daytime. F1 on the bottom from 150 to 250 and F2 on the top from 250 and above. These layers are mostly dominated by atomic oxygen, and they are the highest ionized layers of the ionosphere because they are at the top, so they're getting all that UV from the sun, and they are split during the daytime due to a difference in the density and the constituents to a degree, but also that F2 interacts with Earth's magnetic field and leads to a lot more dynamic interactions. On the other side, on the night side, the D region sort of disappears because our main source of ionization there has left, the sun is gone, and it has that increased recombination. The E region does weaken, but somewhat persists depending on your geomagnetic activity, if you've got any cosmic rays, if you've got any meteors ablating, there could be some residual ionization there. The F region, we say, becomes one layer. More specifically, the F1 layer disappears as the radiation and ionization has left, but the F2 layer does persist due to polar polar transport of charged particles from the day side, and the F2 region is very vital for nighttime radio communications to still have the reflections we need off the ionosphere. Also, for some neutral atmosphere interactions, not an expert, but I still wanted to put these in there as they're pretty important. At the bottom, we've got the troposphere where all of our weather is, and we've got weather activity and upward propagating waves that lead to some interesting ionization patterns upward in the formation of sporadic E. Similarly in the stratosphere, but we've also got these specific things called sudden stratospheric warming events that influence the tides and ion drift patterns above. In the mesosphere, sort of on the bottom near the D region, we've got nice wave activity and meteor ablation and all this stuff creating turbulence and upward energy and metallic ions and really giving all those constituents into the D region. In the thermosphere, big layer, this is where we've got the E region, the F1, and the F2 from the sun ionizing the thermospheric layers. And we've got all these neutral winds and wave influence from the mesosphere that leads to some ion-neutral collisions that trigger little electric fields and energy exchange between the particles in that layer. And at the top, we've got the magnetosphere, where all the magnetic field lines are, and electric fields, field-aligned currents, leading to auroras, irregularities, plasma bubbles, all this exciting stuff. Very interesting at the high altitude ionosphere. So while we do have those vertical layers, I also wanted to talk about the specific regions on the Earth in terms of latitude. I'm starting in the middle with the mid-latitude ionosphere, as it is the least complex in my opinion. The mid-latitude ionosphere stretches from about 15 degrees to 60 degrees in latitude. It depends on who you ask. That's kind of how I personally define it. The mid-latitude ionosphere has the most well-defined layers and is relatively stable and predictable, but we do still have some key features that influence it. Those being particularly sporadic E, I think as I mentioned on the neutral atmosphere slide, this is formed by, these are increased ionization layers that are sort of compressed and formed by the wind shear of metallic ions. They can occur at other latitudes, but they are more common around the mid-latitude region. And a structure that I personally have studied a lot is the ionospheric trough. This is a explicitly, generally, nighttime feature that is a big depletion in the number of electrons that sort of stretches along the night side and is characterized by what season it is, how much geomagnetic activity you have, the local time, the solar cycle. It really depends on the auroral activity, honestly. Getting a little more dynamic, we have the equatorial ionosphere, roughly between 15 north and south latitude. This receives the most solar radiation as the sun is, right above there almost all the time. So this is the most intensely ionized region, and what this leads to is these two distinct ionization bands occurring at roughly 15 north and south latitude. This leads to the equatorial plasma fountain effect. So if we remember our right-hand rule from physics, we've got an electric field that flows eastward at the magnetic equator and a magnetic field that flows south to north. So that generates an E cross B drift at the equator that lifts plasma upwards along these diffuse lines, and they are forced downward either by gravity or pressure or by layers, and this creates those bands. I have a plot later that'll show them better. We also have these things called equatorial plasma bubbles, which is just little depletions in the E region that sort of are propagated upward by this E cross B drift, and this leads to a little depletion that is now suddenly in the less dense but also higher ionized, like upper E region, lower F1 region. Most complex is the polar ionosphere. Yes, I kind of put this plot in there to scare you, but also this is everything that's going on there. This is above 60 degrees latitude, highly sensitive to solar and geomagnetic activity, as this is where all of your magnetic field lines are converging and going down through the ionosphere. So we've got all this different stuff, such as plasma convection patterns. That's the pattern that plasma flows on, essentially, in the polar caps. That is driven by the interactions of electric fields with the magnetic field. It sort of flows like this, and this is what leads to the plasma transport from the day side to the night side that sustains the F2 region. We've got particle precipitation of enhanced and charged particles entering into the ionosphere. We've got plasma density structures such as polar cap patches, enhanced densities, streams of cold plasma called ionization tongues, and of course we've got the auroral oval. This is defined as the ring boundary between open and closed magnetic field lines that is displaced by solar wind, and this is of course where the aurora occur. So why do we care about the ionosphere? We've heard some pretty good summaries already, but I saw this little quote that I liked that is, when the aurora is strong, your signal may be wrong. So the ionosphere being a layer of ionized plasma, almost all satellite signals from GNSS satellites must travel through this ionosphere. These are signals that we need for very precise positioning, navigation, timing, and other instruments have to experience this as well. And so these signal waves do interact with the electrons in the ionosphere, just as any radiation does. And they experience reflection or bouncing, refraction, the bending, diffraction, which is dispersion, absorption, and all this different stuff that influences your signals and causes delays and errors. And on top of that, with the ionosphere itself, as we saw earlier, if you have enough buildup of ionization, you can get radio blackouts and even power outages on the surface if you've got a strong enough solar storm. So it's important to know what's going on up there. How do we study the ionosphere? There are a whole bunch of different methods. I'm sure there's even a few that I missed in this slide, but we've got things from ionosondes, which are upward-facing sounders, incoherent scatter radars, GNSS signal monitoring, HF radio observations, magnetometers measuring the geomagnetic field. These are all just stuff on the ground. We've also got space-based methods of satellite-based in situ instruments. We've got radio occultation from GNSS satellites to low Earth orbiting satellites. That's just a direct signal. And other methods such as sounding rockets, just short in situ measurement missions, and existing ionospheric models that we've used from previous data. So me being from a lab that specializes in GNSS methods, I'm going to give you a brief little overview on how that works and how we look at the ionosphere. As a general overview of what GNSS is, it's just multiple satellite constellations with global coverage that are responsible for the positioning, navigation, and timing, as I said. An example that most people think of is GPS, the Global Positioning System, but we've also got BeiDou, Galileo, and GLONASS. Most of these satellites are in a middle Earth orbit, or MEO, which ranges from 2,000 to 36,000 kilometers, but most of these satellites, I believe, sit in 20 to 25,000 kilometers orbit. They are arranged so that there's at least 4 to 6 satellites visible everywhere, and they transmit signals along the L band in multiple frequencies typically, so we can get better precision in those signals by comparing how the frequencies are adjusted differently from the ionosphere. That's on the next slide. So the way that we use these signals to look at the ionosphere specifically is, I really like this quote from a professor in our department, that is, one man's error is another man's signal. So in turn, the number of free electrons along a signal's path does cause code delay and phase advance, and you might not receive your signal at the time you're expecting or in the correct phase that you're expecting. So you can calculate the ionospheric delay in this signal to correct the pseudo-range for navigation. But in turn, you can use this ionospheric delay on the signal to calculate the total electron content, which is the total number of electrons along a signal's path. So I put that equation there. It's just the difference in 2 frequencies and 2 phases of the satellite signal. That's part of why we did dual frequency. There is a way to do it with 1 frequency, but it's a little cumbersome, so this is much more common. It's commonly expressed in TEC units, that is 10 to the 16 electrons per meter squared, and this allows us to visualize the state of the ionosphere by how many electrons there are. So here's our specific examples where we can use ground receivers to construct global maps of total electron content, which is what I have on the bottom there. You can also see those ionization bands along the equator, like I was mentioning. And if we have other horizontal or in situ information, we can derive the electron density, which is the electrons per meter cubed in 1 cubic region rather than the total number. If we have that information, we can also construct vertical profiles like I have in the top right to see how the number of electrons is changing with altitude. So using maps like this, we can study various structures and phenomena and where they are occurring to hopefully predict ionospheric response to space weather events in the future. So a little on my specific research, I do three-dimensional modeling of the ionosphere using those electron density measurements as I stated, and I'm trying to produce an updated model with a bunch of new and exciting satellite signals like reflected signals and low elevation signals to achieve better in spatial temporal resolution, since it's hard to get that from one source, but it's a lot nicer if you can combine a whole bunch of sources that bring different advantages. So if you'd like more details on that, I have a poster on Tuesday. And I figured if you are really interested in the ionosphere and you'd like to study it a bit yourself, I included some textbooks here. I know textbooks aren't always the most accessible, but I believe that the understanding space weather and the physics behind it is available for free online at least. The GPS book maybe, but the two on the left are a little more math heavy, but they are the space weather books that study everything from the sun almost to the surface, all the atmospheric effects, including the ionosphere. They're just a little more math heavy, so they're good if you like physics. These two in the middle, very big, very dense books, but they've got almost everything you'd need to know about radio communication, and that includes the ionosphere. And the one on the right is a more general GPS book, but I really personally like their overview of the ionosphere and how we study that with satellites. And then in case you'd also like to study the references I used to help make this presentation, I did put them there, but I'm sorry, they are very small and didn't even fit all the references I had. But if you'd rather read a paper than a textbook, I've also got those in there. So hopefully you can find the slides online to access those a little bit better. So that's it for me. Thank you.
Thank you so much, Brenna. Great talk. We have time for several questions because we're running a little bit ahead of schedule. So, Erin.
Hi, thank you for the talk. I have a question that how well does E-region altitudes interact with the magnetic field? Because I'm asking in respect of the E-region wind dynamo that's created. And because I remember reading in one of your slides that it's weaker in the E-region and more stronger in the F-region. But the E-region wind dynamo, like, can you talk about that?
So you're asking about how we get interactions between the E-region and the magnetic field?
Yeah, like how well and how strong is it?
Ooh, not as strong as the F-region, for sure, but off the top of my head, I don't know this phenomena in particular, but off the top of my head, I'm guessing it's either particle precipitation from effects in the F-region trickling downwards, or it comes from compression of the magnetic field from solar wind that may be pushing the effects to lower altitudes.
Because this is the phenomenon which helps atmospheric tides go from the ground up towards the F-region.
Okay.
So I was wondering, like, if it's dependent on like a particular time when a geomagnetic storm occurs, or
100%.
Or is it like a more consistent throughout the year? Like, yeah, that was my question.
Okay.
I have a relatively simple question. I've heard, hi.
Hi, sorry.
I'm right up here. I've heard the phrase metallic ions a couple times.
Yeah.
What metals? Are we talking like astrophysical, anything higher than hydrogen? Are we talking about iron?
I think
What's metallic?
I think we can have iron. The metallic ions in the ionosphere are typically introduced from meteor ablation, which is just any meteors that burn up in the atmosphere, those get ionized in the process, and those metallic particles break apart. I know iron for sure is part of it, but I'm guessing it's almost anything iron and lighter would be my guess. If that hopefully answers that.
Hello.
Hi.
Thank you for the talk. It was great.
Thank you.
I was just wondering about the electric field, because you mentioned that there's an E cross B drift that's like counteracted by gravity.
Yeah.
So there's an electric field sort of equatorwards. So I was just wondering where that electric field comes from, why it exists.
I believe, this is a good question, and I should have studied my physics a little
Can
more.
I just add?
But
I'll just add that from the like GEM magnetosphere side of things,
Yeah.
we learn about like a co-rotation electric field that would be a radial electric field. So it
Yes.
sounds like at lower altitudes you've got something different going on, which is why I was
Yes,
asking.
there is both a co-rotating and, what is the word? I wanted to say general electric field, but that's not accurate. But there are multiple electric fields at play that do definitely different things when mapping, charged particles from the sun. They split where the ions go and the electrons go, but I want to say it's generated from interactions of the magnetic field, but I'm not 100% sure on that.
Okay,
But
thanks.
there is a separate one. Yes, they are different.
Thanks anyways.
Yeah.
I have two brief questions.
Yeah.
The first one is, you mentioned that the layers of the ionosphere are different on the day and night side. So what happens at dawn and dusk? Is there a region where the layers are just kind of squishing down?
It's definitely not a sudden change. Yeah, there is some carryover on each side. Like, part of the ionization of the F2 region can be carryover of charged particles from the day side carrying over through dusk. They are not a sudden change. So yeah, it is a fading, I guess, effect, if that makes sense.
Okay, that makes sense.
Yeah.
The other question I had was, well, also somewhat about the structure. You said that the ionosphere is influenced by solar and geomagnetic activity. Does that change the layers too, or does it have more to do with changing the particle dynamics within them?
It's more about the particle dynamics within them, although I believe some layers, like the F2 layer, if the magnetic field becomes compressed, then things in the F2 layer are a lot more interactive with the magnetic field lines, and it can change, how things are drifting and transporting in the layers. So I guess, yeah, it's the latter that you were guessing.
Okay, thank you.
Yeah,
All right, thank you so much, Brenna.
thank you.
Up next is Jody McLennan from University of Iowa to talk about magneto-iono-thermosphere coupling, or iono-magneto-thermosphere coupling, or whatever order you want to put those words in.
Hi everyone, I'm a third-year PhD student at the University of Iowa. I study the aurora, and it's a very neat way to see the connection between the magnetosphere and the ionosphere. I just wanted to start off by saying that there's a lot of mechanisms to couple the magnetosphere and ionosphere and thermosphere, and I don't know them all, like a whole lot, but I will go into at least a couple of them from more of the point of the magnetosphere side of things. So to start off with, you might hear this at the conference, but the magnetosphere, ionosphere, thermosphere is often referred to as a system of systems. So you have the magnetosphere, you have the ionosphere, and they're coupled together, and that coupling can be like a nested system of systems, and it can be very confusing of what causes what and what drives what sort of effect. And so the effects are can be very tricky to untangle. So this is a problem that is trying to be addressed right now. But thank you to the previous presenters who have defined the thermosphere and ionosphere so well, so I won't go too much into that. But on the magnetosphere side of things, I'll go briefly over the different parts of the magnetosphere. So to start off with, the magnetosphere is any part of the area around Earth that is affected by the Earth's magnetic field. So I like to think of the magnetosphere as a pebble in the ocean of the solar wind. So we have the solar winds coming in from the left here. Let's see if I can, there you go. And it reaches our Earth, and because the solar wind is supersonic, it creates a shock wave once it reaches the Earth's magnetic field, and that's the bow shock. Next, we have the magnetopause, which is the boundary between the magnetic pressure of the Earth's magnetic field, or where that pressure of the Earth's magnetic field balances with the solar wind's dynamic pressure. So you can write out an equation for a pressure balance and find how far out away from the Earth the magnetopause is. The magnetosheath is the region between the bow shock and the Earth's and the magnetopause, and it's often filled with turbulent plasma. I think later talks will get into that. The lobes are a region of less dense plasma above and below the plasma sheet. The cusp is a funnel-like structure around the poles of the Earth, and they're primarily where we have open field lines, where the Earth has a direct path to the solar wind and the magnetosheath, so we get plasma coupling between those two regions because of the cusp. And then the plasma sheet is in the equatorial plane, and it's surrounded by closed field lines and consists of hotter plasma. And the plasmasphere is, you can think of it as an extension of the ionosphere, and it's consisting of more cold plasma. All right, so to start off with, we're going to talk about the Dungy cycle, which is the main driver for the solar wind, magnetosphere, ionosphere coupling. I'm going to start this movie because it takes a second, but we start with magnetic reconnection on the day side. So if we have a northward pointing intermagnetic field, and then we have a southward IMF, and then a northward Earth's magnetic field, we can get reconnection on the day side. And that allows for plasma to switch between the solar wind's magnetic field line to the Earth's magnetic field line. That plasma will be dragged over the Earth by the solar wind. Let's see if I can play this movie again. And eventually there will be enough pressure in the tail region, so behind the Earth, and that pressure will build up, and then reconnection will trigger so that all that magnetic tension that was stored up will be released as kinetic energy, and that field line will be pulled towards the Earth in a more dipolar configuration. And then now that new magnetic field line will circle back to the day side, and the cycle continues. And this is more effective if we have a southward IMF, but we can still have a Dungy cycle with a northward directed IMF. So one result of the Dungy cycle is we have a two-cell convection pattern over the polar cap, and the polar cap is just, it's where we have high latitudes around the open and closed field line boundary, which I've highlighted in these green dots here on this little figure. So as the Dungy cycle is pulling all that plasma across the cap, it's dragging the ions along with it. And so we have this anti-sunward flow across the middle of the polar cap, and then we have a return flow at lower latitudes. And one thing to note is the distribution of the equipotential lines that result from the convection. So, we have an electric field that is generated as a result of the Lorentz force. So we have a magnetic field pointing down, and we have this motion of the plasma, which generates electric fields. So a project by SuperDarn was able to map out the equipotential lines of this two-cell convection pattern for different IMF orientations. So you can see that for a northward IMF, we have very low convection I think I'm pointing in the wrong spot. Okay. Yeah, there we go. So we have less efficient convection, but for southward IMF, we have a lot more convection. And then the distribution of the two sub-convection pattern changes depending on if we have a more BY-oriented IMF or in the negative BY direction. Okay, so now we're going to go into the current systems. So first off, we have field-aligned currents that will flow parallel to the magnetic field lines. Usually electrons will be carrying these currents. The two that I'm focused on right now are the region 1 and region 2 currents. So the region 1 will close over the magnetopause, and then the region 2 will close from the ionosphere around the partial ring current, which I'll touch on a little bit later. So we can map these current systems down into the ionosphere as well. So this is the same picture of the polar cap. We have currents coming out from the region 2 currents. So those are on the closer magnetic field lines, and they're more equatorward. So they're coming out of the page on the dawn side and then returning into the page on the dusk side, and then it's the opposite for the region 1 currents. And then just so you know, this schematic is not as nice as like the data actually is, and even this picture is not typically what happens. This is a very like nice, clear defined region 1, region 2 currents, but you can see that they kind of like snake around each other. They kind of overlap, which creates for some interesting dynamics. And then there's also currents perpendicular to the magnetic field. So we have the Hall current, which flows in the opposite direction of convection. And the strongest parts of its current are the eastward electrojet and the westward electrojet on the dawn and dusk sides. And they're caused by an uneven response to the E cross V drift. So ions will collide more frequently with the neutrals, slow them down. The electrons will be a little faster, and that creates a current. And then the Pedersen currents will connect between the region 1 and the region 2 currents. So they'll go over the polar cap, and then they'll also span the auroral oval, which is between the region 1 and the region 2 currents. So after this brief overview, these currents will combine together to create a closed current system. So there's a couple of them. The first one is the one on the left. So we have current flowing over the magnetopause down via the region 1 currents through the ionosphere back up. And that's just connecting via the Pedersen currents over the polar cap. The figure on the right shows a current system that connects the region 1 and the region 2 currents via the partial ring current. So the partial ring current is formed by electrons drifting east and ions drifting west as a result of the gradient and curvature drifts around the Earth. And this will create like a semicircle current. And where it closes in the ionosphere is those spaces around the aurora oval between the region 1 and the region 2 currents. So then we have another closed current system, starting with the Chapman-Ferraro current. That's a current that goes around the nose of the magnetopause. And then as we look tailwards, it continues around the magnetopause, but then closes through the crosstail current, which flows across the plasma sheet. But sometimes that current can be diverted during some storms. So substorms, there's a lot to say about them. You'll probably hear about them a lot at this conference. I wish I had time to talk about it, but substorms are associated with intensified currents, intense aurora dynamics and displays, and where the crosstail current gets diverted, so it would get diverted into the ionosphere in the midnight sector down here. So now that we have current systems, they would need to close through the ionosphere. And what determines where they close is the conductivity in the ionosphere. So conductivity is determined by electron densities, collision frequencies, and the gyro frequencies of the ions and electrons. And precipitation will enhance conductivities. So during storm times, we'll see an enhance of precipitation, and we'll see an enhance of currents as well. So the Hall current sits slightly below the Pedersen current. A way to pull them apart is to write them out in terms of the directions of the E and the electric field and the magnetic field. It's also worth noting that the parallel conductivity is going to be much greater than the Pedersen and Hall conductivities at any altitude. So I've been talking about how the magnetosphere affects the ionosphere, and there's a lot of driving factors that do affect the ionosphere, but it can also be true of the reverse. So there is a coupling system called ion outflow, where when we have plasma motion along the magnetic field lines, say we have a current going along the magnetic field lines, that's going to heat up the plasma, causing it to lift up. Some of those ions are going to escape, especially H plus and O plus, and that will populate the magnetosphere. And this is especially prevalent during storm time. Okay, so I'm going to touch on ionosphere-thermosphere coupling, but more from a magnetosphere point of view. You guys already heard a lot about that. So I won't really go over this because, again, we've already covered it, but basically we have layers in the ionosphere. They are sourced by photoionization, and or the ions and electrons are sourced by photoionization, electron precipitation during the night. And during the night, those ions and electrons will recombine with neutrals, and those recombination rates determines which layers stick around and which layers don't. So one coupling factor between the ion and neutral populations is collisional coupling. So the extent of collisional coupling depends on densities. It can be a source of heat and momentum to the thermosphere from the convection pattern and currents in the ionosphere. And we also observe neutral wind dynamics that will follow the convection cell pattern. So we actually see that in the data where we have ions and neutral particles coupling together to follow those convection cell patterns. And this figure on the right is just a demonstration during storm time. So these dark lines, or thicker lines, they increase in temperature compared to non-storm time, and this is true for both the ion and neutral population. And then my last point on ion-neutral coupling is that energetic precipitation can also change the chemistry of the atmosphere. So NOx and HOx can be created from energetic aurora or energetic precipitation. And when that NOx and HOx transports downward in altitude via the polar vortex, it can destroy ozone. And ozone is a good regulator of the atmosphere. And it will regulate temperature, circulation, also large-scale weather patterns. So it's an important part of the coupling between the magnetosphere and the ionosphere. So some open areas of research. How do we improve the mapping between ionosphere phenomena back up to its corresponding dynamics in the magnetosphere? What's the role of the ionosphere in the magnetosphere dynamics? How does precipitation affect the neutral atmosphere? And how do we improve our modeling for complex system of systems when we have a hard time dissecting what caused what? And there's also, I guess, an issue of we have a lack of measurements in the ionosphere, which is roughly from like 80 to 200 kilometers This is a region of altitude where we don't have a lot of in situ data because it's too low to get to by satellite and too high to get to by weather balloon. So it's not necessarily in the form of a question, but it's something people want to address. And then there's a lot of acronyms that get thrown at you at this conference. I learned a new one today, MLT. I always thought of that as magnetic local time. I didn't realize there was another definition till today, so that was very interesting. And then here's some GEM focus groups that deal with MIT coupling. And then here's some references I used. I starred some review articles that were a good place to start looking at this topic. And that's all. Thank you.
All right, great talk. Thanks so much, Jody. Any questions? I see one over here that I am rushing to now.
Thank you for the great talk, Jody. I was wondering, when you were talking about the Hall and Pedersen conductivity, you mentioned another current system that has a higher conductivity. Can you, I missed what current system that was, and can you talk about why it has a higher conductivity?
Yeah, thank you, Andy, for the question. So we have the Hall and Pedersen current conductivities in the red and blue lines here, and then the parallel conductivity, so that'd be parallel to the magnetic field, is much greater than the Hall and Pedersen conductivities. And I think that's just because particles are able to move more easily along the magnetic field lines, and they're more easily, there's more, I guess, like flow, you could say. And I think, that's as far as I know.
All right, any other questions? I see one behind me.
Hi, Jody. So first of all, very nice presentation. My question was, so I saw the convection patterns that were modeled by Thomas and Sefford about the BY and BZ asymmetry. So my question is it just BY and BZ components that we should be looking at, or are there any other factors that are important if we want to look at the plasma cross-polar transport? Can you talk more about that?
Yeah, that's a really good question. I think people are starting to look into the BX component, which would be towards or away from the Earth. I don't know too much about its effects on the two-cell convection pattern. So that'd be interesting to look into, but I can't really speak on that one,
Hi, I have a question. So we know the Earth pretty well. How would you expect the current system in another kind of planetary magnetic field, say Jupiter and Saturn, or even more extreme Uranus and Neptune magnetic field?
Yeah, that's a really interesting question. I know Jupiter has a different magnetosphere, or I guess its equivalent, magnetic field structure coupling to the solar wind. So we have the Dungy cycle, but they also have another coupling system, which I'm forgetting the name of, but it has to do with the rotation.
It's co-rotating field.
Yeah,
it stretched the dipole, something like that.
Yeah, that sounds right. And so, I don't know about the current systems on those planets, but I would assume they would look different because of that. And Uranus's magnetic field being tilted from ours would also be very interesting to study.
Thank you for the response.
Thank you.
So unless there's any other questions, let's thank Jody again. And we'll we'll go into our next 20-minute break. Currently on the schedule, it says that there's meditation, but Bagrishi is not here yet. That will be happening from the 2:20 to 2:40 break in the soft skills room. But it's break now.